Hi everyone, I'm Tim. I'm from Mercedes-Benz Tech Innovation. I'm a software engineer slash architect, and I'm also part of a S-CORE team, which you've heard of just right now. Today I would like to talk about vehicle diagnostics for the software-defined era, and also about SOVD in scope of Eclipse S-CORE. Let's start with a quick overview of what we're going to see today. So first, I would like to have a soft introduction into the topics and really get the point across why diagnostics matter and also why they matter today even more than maybe in the past. Then I would like to move on and show a little bit what SOVD is about and what some of the core features are for you guys as a refresher. And then I would like to take a deep dive into the diagnostic concept that we have right now in S-CORE. Thilo showed a couple of the feature requests earlier. And yeah, diagnostics is one of those features that are being proposed right now. And there are some high-level thoughts about this, which I would like to share with you. And last but not least, we will have a quick outlook and talk about now what you can maybe from yourselves, but also from the S-CORE project. So let's get started with diagnostics. So diagnostics are really at the core of the entire vehicle life cycle. It's not just about development or after sales. Diagnostics are part of the vehicle from its development to production all the way until it basically is destroyed in the end. You can see here some of the main application scenarios and use cases of diagnostics, and I will just give a brief overview so that you can see how diverse this topic is. First of all, we require diagnostics as part of the engineering process, so we validate and debug ECUs as part of our daily work. Then during manufacturing, of course, we need to flash software, and we also configure the vehicle and the ECUs for variant coding. In quality assurance, we analyze field issues. In after sales, one of the main use cases, we read and clear and also interpret fault codes, but we can also trigger software updates and use it for general maintenance and also fault analysis. In fleet management, now more than ever, over-the-air diagnostics is an important topic to do over-the-air flashing and updates. For homologation, we need to fulfill regulatory requirements. For testing, of course, we use it in our automated test benches that we use. And then for digital services, it's also a core part to enable features that were purchased afterwards by the customer to enable them in the field. Okay. So as we're moving towards the era of a software-defined vehicle, or we're already right into it, right? There's also a shift in requirements. And there's also a shift in requirements, especially for diagnostics. So for example, we're moving towards more of a zonal architecture, towards centralized HPCs. OTA becomes one of the core needs and a non-negotiable, and also the developers and change, and also the expectations of the developers change, right? They require faster and scalable onboarding. They require API-based development, and I don't think I say too much if I say that most developers don't really want to work with modeling tools anymore. So that's also why some of the legacy assumptions that we had in the past for diagnostics aren't really true anymore, and we also need maybe a better approach. So on the top left, on the bottom left, you can see a small comparison table where you can see some of the legacy assumptions that were maybe made with UDS, like for example, with a config-based approach, with ODX files and tools, with session-based CAN tester model, with ODS-specific UDS interpretation, where every OEM had a slightly different variation of the UDS standard, also manual onboarding and tool-driven diagnostics in general. This is also characterized by having many different clients and many different tools for production, for engineering, for after sales that basically do all the same thing, but are different tools, right? And basically all of this isn't really scalable and acceptable today. So we have a very fast changing industry. We need to scale over multivariant ECUs, especially on HPCs. That becomes more important. Also, cloud connectivity becomes an integral part. So the solution for this is basically SOVD. Most of you probably already have heard of it. SOVD stands for Service-Oriented Vehicle Diagnostics, and it was developed to address exactly those gaps that we see here. So SOVD is characterized by self-descriptive API, so you can discover diagnostic capabilities at runtime. You don't need to know beforehand what capabilities are provided by the ECU, which makes also the tooling and the client architecture much more easy. Also, portable clients, as mentioned, you have much easier tool chains, you have standardized endpoints, and then you also use cloud-ready and scalable technologies like, for example, HTTP, REST, and JSON, which comes with a couple benefits that we can see in a little bit. And still, you can take the legacy systems with you because UDS will not go away, especially if we think about microcontroller. I think we can all agree that it will still be here also in a couple of years. So we also have the possibility to really bridge the gap between those two worlds. And the result of a key takeaway of this is diagnostic used to be a tool-driven configuration of ECUs. Now it really is a platform capability, a capability of the middleware and the platform stack. And that's also why we see it as a strong candidate for S-CORE and also as basically an important part of a holistic platform software stack. Diagnostic. Now let's take a little bit of a deeper look into SOVD. So SOVD is a service-oriented diagnostic protocol. It uses standardized REST APIs and it exposes the diagnostic capabilities through those APIs. The APIs are self-descriptive. So again, you don't need to know beforehand what the system provides in terms of capabilities and services. And of course, it's also machine readable. On the left side, you can see a brief schematic overview of how a SOVD-driven diagnostic system could look like. You have a vehicle, in this case, with 2 HPCs and a ECU, and you have a diagnostic server or SOVD server at the core, which basically is just a web server. You have different apps that you can connect to diagnose, and also a classic diagnostic adapter, which will be used to bridge the gap between UDS and SOVD. As you can see here, also, you have 3 different SOVD clients, which are used in different contexts, but are basically the same. So you have an offboard tester, a remote tester, or also an onboard tester. And here we can also see that we consolidate that much more than what it was in the past. The key advantages are faster integration, so you don't have any modeling anymore. You have a code-first approach, which is not just nice for developers, but is also much more scalable in modern systems and brings you all the benefits of modern coding and CI pipelines that you can think about. Again, self-descriptive schema, and you can discover that capabilities during runtime. The technology is Ethernet first and cloud ready. So because you leverage the proven and used web technologies, not only is it very easy to integrate it into connected backends, but you also get security out of it by design, right? So you can leverage the proven security features that are not just used in the automotive industry, but in the technology or web industry as a whole. Examples are, for example, HTTPS, OAuth, or web certificates, and you can use that for authentication and access control. So that makes it also much easier and seamlessly integrates basically the backend, the vehicle, and the development environment. And last but not least, it's open and extensible as a standard. So SOVD is defined in ISO 17978, and from our perspective, it makes it a prime candidate to be part of S-CORE and also provided as part of such a offering. And here just a quick list of additional capabilities that you may or may not be aware of. So if we talk about diagnostics, most people think about fault codes, right? Because that's what you typically interact with. But we have much more like ECU discovery in the system. So you connect the vehicle, you want to know what ECUs are in there, especially when you talk about different variants or vehicle lines. That becomes interesting. You have a self-descriptive metadata, of course, fault codes, live signal monitoring. If you want to diagnose something and you want to have a live signal stream, that can also be helpful if you, for backend use cases. You have, of course, state encoding access. You can execute diagnostic routines, read VIN info, do software updates, logging, both data handling, and then, of course, classic diagnostic adapter and picture exercise. Nice. Now let's take a look at the S-CORE diagnostic concept. What you can see here on the right is right out of our feature request, and that we have created as part of S-CORE. Unfortunately, I don't have a QR code, but I have a link at the bottom, and I'm pretty sure you guys can find it. Otherwise, you can also ask me. So it's publicly available with not only this picture, but also a lot of text and explanation, and you can leave comments if you think something is a good or a bad idea. But let's take a look. So this is basically what we envision as part of the S-CORE offering for diagnostics. You can basically cut it or separate it into three different parts. You have a top-level part where you interact with your application, so where you feed data into the system. Then you have a core part, so the diagnostic system itself. And then the bottom part is basically the interface layer to external devices, like, for example, SOVD clients or also UDS-based testers, ECU, and so on. So now I would just like to walk through this with you from top to bottom so you can get a better understanding what the idea is and also what we're planning to do here. And if you look at the very top, I hope you can read it, we have apps and activities. So activities are what Thilo showed beforehand, part of FIO, so part of this execution graph, but you can also have any app that you have in your system independent of any of the other S-CORE stuff. We will provide a fault library, which basically gives you, from an application perspective, an interface to interact with a diagnostic system, to feed fault data into the diagnostic system, which can also result in automatic logging, for example. But it also gives you the opportunity to do fault debouncing and custom fault logic. We think it's a good idea to have this with the application, since most faults are application dependent and also context dependent. So people working on the application will probably know best where the fault is coming from and how to handle it and how to fix it. And also this scales much better in a decentralized way. Then we have a diagnostic fault manager, which just basically collects all the faults and all the system states, stores them in a diagnostic database. There you have typically like a DTC ID, a fault ID, you send out some metadata and also some error enum types, like for example, debug and severity levels and so on. The diagnostic fault manager is connected to the SOVD server. As I explained before, the SOVD server is basically just a web server which executes routines or gives you the capability to expose data and handle requests. So for example, you can read out fault data that is stored in the diagnostic database. You can also execute routines, which are here called service apps. So we will provide more of like a generic type of that class. And then you can have your own implementation. Like for example, for flashing, you could execute a SOC vendor-specific flash routine if you want to have that. You also have the capability to do configuration over the S-CORE configuration management system, which is handled in a different feature request. And you also have authentication and crypto built in. As you may notice on this arrows here, you have sometimes SOVD, but also a lot of IPC. So you can see that this is also based on the S-CORE IPC solution. This will act as a baseline for that. The SOVD gateway is basically just a gateway. It aggregates your interfaces. And then we move on to the classic diagnostic adapter. This gives you the opportunity to also diagnose UDS-based ECUs and like, for example, microcontroller or other legacy ECUs, and also have that as part of your system. The UDS to SOVD proxy is basically the same, just in reverse. So if you have a UDS tester and want to diagnose your system, like for example for OBD2 use cases, that is required, and then we will also offer a SOVD client. And what I forgot, just like for your orientation, the dotted line means it's not in scope of a diagnostic feature request, and the solid line means it is in scope. So for every solid line box that you can see here, a much deeper follow-up feature request or also contributions will follow. So this is really the high-level target that we're working towards in S-CORE. Now let's also set that into context. And here the statement again: Eclipse S-CORE aims to provide a free and open source implementation of SOVD following the architecture that we've just seen. Here you can see again the architecture diagram that Thilo already showed. The red box basically just shows you where in the stack that will be that will fit basically, and what components are part of that. But it's, to be 100% accurate, is not just diagnostics but also fault management in general, because that fits well together. Looking a little bit at the timeline, I think we've seen it also in the previous presentation. 0.5 more towards this year, 1.0 more towards next year. Diagnostic is part of the scope of version 1.0, so it will be more targeted towards next year from a timeline perspective. Here again, some core benefits of why we think this is a good idea and why SOVD and diagnostics should be open source. First, as discussed before, we want to collaborate on non-differentiating software parts, and we think that that diagnostics are a very good example of such a non-differentiating software part. We also want to accelerate adoption across the industry and also provide an implementation that is really, as a OEM agnostic for, and is therefore of higher quality, and also, as we've seen in the very beginning, more secure. Because of course this introduces also a whole lot of different security attack vectors that we don't have so far, right? So these are reasons why we think it's great to do this in FOSS. And now benefits for you if you would like to adopt it. So first, you can boost your developer productivity because you have a code-based workflow and you don't need to model in tools anymore. Then if you have a SDV architecture, this fits seamlessly into it because it fits seamlessly to a service-oriented architecture that is mainly Ethernet-based and connected. And as I mentioned before, it's cloud ready. If you want to connect your backend, this is where to do it. Okay, I hope you guys could follow me so far. And now let's move on to the last slide. So this is a little bit of an outlook, but also a call to action to you guys. We have planned the next steps, but you can also be a part of it. Right now is the time in the project to actively contribute and also to shape this. So if you disagree with something, come join us in the S-CORE architecture team. Let's have a talk about it and contribute. The next steps that we've planned so far is we want to define and finalize the diagnostic concept for version 1.0, because there's a lot of depth to this topic. Second part is we set up a diagnostic feature team. I think we've seen that also in the previous presentation, how that works from an organizational standpoint. And last but not least, you can expect some contributions soon, which will be led by Mercedes-Benz and ZF. And yeah, I hope you guys enjoyed the talks. And now it's time for Q&A, and that's it from my side. Thank you, guys. Excellent.
Thank you, Tim, for the presentation. I was wondering if the ISO that you mentioned, the ISO document, does it only specify the external API of provided by SOVD, or does it also specify the internal workings of how a software update would need to be applied or
Found. So right now there is the ISO, or better this, in its current state, and it mainly defines the API to make it interoperable with other SOVD systems, and then for the inner workings, that is defined by other standards in addition.
but there are other standards, or can you simply choose whatever you want, like you did with your IPC, for example?
So, for example, there is the ASAM standard that maybe some of you know, and parts of it were transferred into the ISO. So that gives us the opportunity to basically work under the umbrella of the ISO. And yeah, also, just to be frank, the ASAM is also aware of this activity. So from our point of view, we don't see any potential conflicts here moving forward with an implementation.
Are you involved in the elaboration of the ISO standard?
I'm not involved in the ISO.
Or Mercedes-Benz, like I mentioned. Yeah, okay. Okay.
The question that I was asking.
If nobody else is asking, I'm asking. Thanks, Tim, for the presentation. I would just like to clarify, you've been mentioning on your last slide that we may expect a contribution soon, and Mercedes and ZF are driving that. Is my assumption right that you're going to contribute that in the form of a separate project, which then is going to be integrated in SCORE? But for example, and I believe there might be others in the world who would also be interested in, and they can consume that SOVD project or technical building block as is?
Yeah.
Or is that only in SCORE?
No, exactly how you described it. So there will be a separate project as part of the Eclipse SDV umbrella, and S-CORE will act as a integration repository. But what we should also mention here is that, for example, the architecture and some of the requirements, and also what we see in the development workflow with requirements and so on, will be driven by S-CORE.
Oh, awesome. Thanks.
So to emphasize that point, maybe as you said, Ansgar, we will launch a new project that I think we will enter public revenue by end of this week. It's only few. And so we will implement everything at SOVD specific that project. And as said, slowly together with set up that project. But we are very, very happy if there's other people interested in that. So that you would join us in that endeavor to create an open source implementation and good widgets of implementation of SOVD. And the other aspect of that is, of course, S-CORE needs a diagnostic capability, and we are planning to fulfill that with open SOVD. That saw in the architecture deep dive for S-CORE. We'll bring this to the contribution pit. I doubt that there will be many others, but those. Yeah. But I would say if you are interested in integrating this and making S-CORE, then I think it's sort of special about this. But even more important would be for us that you engage in the upcoming open make SOVD what cool thing, and any contribution congratulations.
Okay. Is there a question from the online?
Yep.
So there's a question from the online audience. As we saw, that answers it. But what's the mandate of Fold API? I hope we don't make the mistake of trying to start plastic of having something like functionally return management in the scope of diagnostic and hence merging the lines between diagnostic and safety supervision.
Yeah, so I would actually just take the answer that was provided by Anita, because I think this answers it perfectly. Should I read it? Or I can read it. So basically, the fault API is just an abstraction and a interface to report faults into the system and to handle faults. And then everything which is safety related is again, it's a topic.
Also, there have a couple of people that are offering to join. So that's very good. So for those of you who are interested, just please reach out to them and make sure we get as many people on board from the very beginning. Yeah.
So Toyota is already in. I'm going to quote you, Ito-san.
Yes, exactly. Maybe let's make a screenshot. Okay, and maybe I have a question. So, how is there any connection with the OpenGUT project that you?
Not Tito.
So there's
That's this is an easy one. The plain answer is no. The longer answer is probably yes. So OpenGUT is a testing framework or any testing, and of course we could use OpenGUT for testing this, right? And if you are involved in the OpenGUT, maybe you already want to get involved with AT, but you're also interested in SOVD, then sounds sorry. So yeah, again, I would encourage you to get involved and collaborate, and then stay on board.
so there's. Thank you again to our speakers. And